Give me a second. I'm trying to go live. Okay. Right. Now we are live. So basically, I'm not going to waste time on the things that we talked about last time. Today we are only focusing on the things that we said we're going to talk about today. Which let's go to them. Right. So we are talking about the conditions that are needed for equilibrium and the contact process, and then the stages. Are you ready? This is what we are focusing on: the Haber process and the contact process, and what happens and what we must know. Okay? Are you ready? Can you all hear me? Everybody? Can you hear me, students? Am I unmuted? Sibu, can you hear me? Okay, great. So when we talk about the contact process, let's talk about it. Haber process occurs in 5 stages versus the contact process, which occurs in 3 stages. But then, where it is different is that for the contact process, you're going to actually need to know the reactions that happen at every stage. For the Haber process, no, you won't have to. You won't have to know the reactions that happen at each stage. But you must be able to talk about what happens. You must just have an idea of what happens in the Haber process. So let's put it. Let me put it for you. And let me see if this is a perfect diagram. Some of my diagrams are not perfect, but I'm going to edit it right now as we are doing it together so that you understand. So basically what happens with the Haber process is you're going to have your gases come in. So let me put it like this. Yes, this is a compressor and it is going to get from the air. So if I can cut this here, okay, you have air coming in like this and you have air coming in like this. And what comes in is you're going to have nitrogen, which nitrogen is the most abundant. We saw that we have 78% of nitrogen in the air. So nitrogen is obviously from the air. And then we are going to have hydrogen. Hydrogen will come from natural gas. I want you to say from natural gas. So remember our Haber process. You're going to have nitrogen plus hydrogen meeting. And you have 3 like this, and they have a reversible reaction which makes ammonia gas. So this is how easy it is: 2 moles of ammonia gas. This is the easy. So we need nitrogen and we need hydrogen. So you must tell us what happens. This becomes our stage 1. Our stage 1, we are going to have them coming in from the air, and they go into the compressor, which is stage 2. So they are going to be fed into the compressor. Then from the compressor, they do go into the reaction. Yes, I don't know. They go into the reaction chamber. So that's fine. So this becomes our stage 3, into the reaction chamber, which you can say stage 3. Then from the reaction chamber, they go into the cooling tank, which is stage 4. So this is fine. And then from the cooling tank, this is where you're going to collect your ammonia. So I want to say ammonia out. We can have it here to say ammonia out. Yes. And then what will happen is this: that liquid ammonia which comes out, you're going to have some which doesn't, okay, some nitrogen and hydrogen which did not actually react. So it will just go back. The nitrogen and hydrogen which did not react. I want you to show where it goes back and re-enters this reaction chamber. So it's all right. So let's talk about it. Let's talk about the stages. Let me put the stages. In stage 1, what do you have in stage 1? You're going to have your hydrogen and your nitrogen. If we can say, when we say natural gas, you can put methane, butane. These are the gases that people use. The natural gas. It can be methane. They are the alkanes that burn the most, are the smallest alkanes. So basically, everybody, we want to put nitrogen and hydrogen into our reaction chamber. So we get them first, then we compress them. To compress them means we bring them together. so that we have a lot of gas close to each other. Because remember, we are producing ammonia for mass production. This is the industrial production of ammonia. We are not producing it for one family. No, we are producing millions of it. So we are going to have millions of liters per year. So not in one reaction, but per year. So we're going to say, all right, we get it. Then what do? We put in compressor. So in stage 2, you should say that stage 1 is the pumping of hydrogen from methane and nitrogen from the air. Okay, you pump it. Then in stage 2, it goes into the compressor. And remember, we said that we need 200 atmospheres. That is for the Haber process. 200 atmospheres, and the temperature we'll talk about it, 450 degrees. It is going to happen in stage 3. In stage 3, you're going to put into your tank. Okay, this tank is like your reaction tank. They call it the reactor. In here, you are going to meet layers of iron. Iron is the catalyst here. So you have layers of iron. So this is iron catalyst beds, the layers of iron. And then you're going to make your gas move through them. So it moves through the layers of iron. And it is at 450 degrees Celsius. So temperature happens in second stage. Pressure. Temperature happens in third stage, where you're going to have the pressurized gases going into a tank. And this tank is at a temperature of 450 degrees Celsius, and it has the iron catalyst, the layers of iron catalyst. And this is where your reaction will happen. So in this reactor, this is where you are going to have your nitrogen plus your hydrogen coming together to give us ammonia. Don't let me down, students. I'm counting on you to give us 2 moles of ammonia gas. And that ammonia gas, we then pass it through the cooling tank, where it will be collected as liquid ammonia at the bottom. But then the unreacted students, the unreacted nitrogen and hydrogen will be passed back to the reactor. They will be taken back to the reactor. Easy. So unreacted, they are recycled back to the reactor. All right. Anyway, the liquid ammonia goes to the cooling tank, where the ammonia comes as a gas. It passes through the cooling tank. It is converted to a liquid. It condenses, then is collected as a liquid. Thank you. So what are the pressure? 200 atmospheres, 450 degrees, iron catalyst. This is way too easy. This is way too easy now. This is way too easy. 450 degrees. Where does this happen? In the reactor. Iron catalyst. Where does this happen? In the reactor. Where does the reaction happen? In the reactor. This is stage 3. In stage 2, what happens? They are pressurized in a pressure temp. In a compressor, you can say in a compressor. Stage 2, this is where the gases are passed through a compressor. Anyway, why 200 atmospheres? Why 200 atmospheres? Now we are talking about the Haber process. What is the Haber process like? So remember, we talked about Le Chatelier's principle. Le Chatelier's principle, can you tell me? Let me see. I want to talk to you guys as my friends. Let's come on now. You're not going to let me down. So Le Chatelier's principle, we want to talk about how temperature affects the position of equilibrium, how concentration affects the position of equilibrium, concentration, how pressure affects the position of equilibrium, and how catalyst affects the position of equilibrium. Right, let's go for this. How catalyst. So let's, when you are looking at how temperature affects the position of equilibrium, students, what do you look at? What should you focus on? When we want to use Le Chatelier to explain how temperature affects the position of equilibrium, what do we look at? Raise your hand, raise your hand. Somebody raise your hand and tell me what we focus on when we are talking about how temperature affects position of equilibrium. What do we look at? Someone raise your hand. Students, when we want to analyze what happens when we increase temperature, how do we know what happens? If somebody says, hey, I've increased temperature, what happens to the position of equilibrium? What do you say? Students? Oh my days. Are you forgetting? You look at delta H. Come on now. If somebody says you have increased the temperature, what happens? Look at delta H. So that you see if that reaction, if the forward reaction is endo or exo, whatever. Remember, when you increase temperature, equilibrium should fight to decrease it. So it will go in the direction of endothermic. It will go in the direction of endothermic. So let's look at this Haber process reaction. Right. They said the forward reaction is exothermic. They said the forward reaction is exothermic, which means if they give you delta H in the exam, it will be negative something kilojoules. So, students, can you tell me what happens if we increase temperature? In this reaction, don't let me down. If you increase temperature, equilibrium must fight that. It must fight your increase, which means it must go in the direction of decrease. But the forward reaction is exo. If they put exo like this, it means the forward is exo. If they put delta H here, they'll be telling you about the forward. So can I ask you a question? If we increase temperature, students, if we increase temperature 1000 degrees Celsius, what will happen to the position of equilibrium? Will it shift to the right so that you get more ammonia, or it will shift to the left so that you get more of nitrogen and hydrogen? Talk to me. Mazita, what happens here? We increase temperature. What do you expect the equilibrium to do? Chemists, come on now. Mazita? Mazita? Are you there? Okay. Tobo, I see you say the answer. What is it? Where does the equilibrium shift, Tobo? Tobo, you can unmute and say. Hope. Okay, let me ask you this. You did it very well, Hope. Thanks. Let me ask you this. Let me ask this so that I know if you're moving with me. Anita? Mm, it shifts to the what? Yes, Hope. Okay. Anita, Lisha tell you, when you change something, should the equilibrium. Well done. Well done. Well done. Well done. Well done. So let's not. Well done. Let's not make it complicated. So I'm very happy. Anita, remember, equilibrium should fight. Should fight. It should fight. We are increasing temperature. Students, don't let me down, guys. We are increasing temperature, guys. Guys and girls, we are increasing temperature. We are increasing temperature. So the equilibrium should fight us by decreasing it. How does it decrease it? It should go in the direction of endo. it should go in the direction of endo. So the biggest question we have here is, where is endo? Is it forward or backward? Come on now. They told you forward is exo. Come on now. They told you forward is exo for Haber process. Haber process produces heat. Haber process produces heat on its own. It's an exothermic, the forward reaction. So when you increase temperature, you are not improving it. You are fighting it. Because you are going to make equilibrium shift to the left and start to produce more of this. And start to produce more of nitrogen and hydrogen. Because there is no way it will agree with you. It can't shift to the right. We know that it will shift. You increase the temperature, Haber process will go in direction of endo, which is backward. We always run away from this negative sign when you increase temperature. Because if we move here, we are increasing with you again. So if you ever increase temperature, equilibrium will shift to the left. And you're going to start getting more of nitrogen and hydrogen and no ammonia, which is a disaster. So you can't increase the temperature too much to 2000 degrees Celsius and whatever, because you end up having no ammonia. You'll be just producing a whole lot of nitrogen and hydrogen. But then we have another situation. If we decrease the temperature, yes, if we decrease the temperature, then it will fight that. It will try to increase it again by shifting to the right, to exo, to say, hey, exo, produce heat, produce heat. They have decreased the temperature, produce heat to fight it. All right. But now we cannot decrease the temp. So that means it will be good. We'll get a lot of ammonia. It will shift to the right. We'll get a lot of ammonia. That's good. But we cannot decrease the temperature too much, because guess what? Decreasing temperature affects something else called rate of reaction. If temperature is low, the rate of reaction is slow. The speed. Remember, there is rate of reaction and then there is equilibrium. Rate means how fast. Equilibrium is how much is produced. So we cannot have temperature too high, because yes, the reaction will happen very fast, but you produce very little because it will shift to the left. So you produce very little. So we need to be 50-50. We need a temperature 450 degrees. It's not too high and it's not too low. It's not too high, because if it's too high, then what will happen? Then the equilibrium will shift to the left and produce more of the reactants and less of ammonia, which is a disaster. And it's not too low, because if it's too low, we'll produce a lot of ammonia, but way too slow. To be way too slow. So we need a compromised temperature. So why do we have 450 degrees Celsius? Here. Where is it? Why 450 degrees Celsius? So that we have, it is a compromise between yield and rate. Yield means how much you get. So it's 50-50. We are trying to make sure we get a good amount of ammonia. Okay? To get a good amount of ammonia, we need to decrease the temperature. We know Le Chatelier said it will fight you. So if you decrease the temperature, it will fight you and lead to and move to the right, move to exo, to increase that temperature which you are decreasing, which will be good news for us. We'll get more ammonia, but then it will be too slow. So what we'll end up doing, we'll choose a 50-50, which is 450 degrees. It's a compromise, which means it's a 50-50 between yield and rate. So 450, we'll make sure we get a good amount of ammonia and also not too slow. It will be okay. The speed is okay. Why 200 atmospheres now? Why pressure? Why pressure of 200 atmospheres? Why do we need 200 atmospheres? Should I make it? I don't want to make you guys cram. But look here. We said yesterday, nitrogen plus hydrogen to give us ammonia. Yesterday we said, the other day we said, if we are talking about pressure, if you want to know how pressure affects position of equilibrium, you look at the numbers of moles. There are 4 moles on the left, and there are these big numbers here. There are 2 moles or molecules on the right. So, what happens if we increase pressure? Should the equilibrium agree with us, or it should fight us? What does equilibrium do when you change something? It fights you, right? So if we increase pressure, it must fight us by going where there is less. Which side has less to try and decrease the pressure? Which side has less? Lusika, which side has less, the left or the right? Which side has less moles? Lusika, which side has less moles, the left or the right? How many moles are at the left-hand side, Lusika? Can you see in circle there? How many? Lusika, how many moles are at the left? Letty, how many moles are at the left-hand side? Letty? No. Students, can you actually hear me? Anita, can you hear me? So why are you not talking to me, guys? What's the problem? Sibu, how many moles are at the left? At the left, this side. How many moles are at the left? 4. Who's the other one? Aki, how many moles are at the right? Two moles. So I want us to master this. You're gonna meet this anytime. You're a scientist. Don't let me down, okay? We have to fight. Don't let me down. Look at the correct thing. Fight your mind right now. What makes a good scientist is you are a person who abides by the rules. Like, you control your brain. So let me tell you how you're a good scientist. You control your brain such that everything you believe is a theory. You don't believe anything which science does not agree with. For example, if I come and say, when you hit the walls, you are the only one, or when you slap, let me not talk about slapping, that's rude. But let's just say when I slap myself like this. Common sense will say the cheeks did not hit the hand. The hand hit the cheeks. That's common sense. But you are a scientist. You don't live from common sense. In your mind you say, what did Newton say? For every action, there is an equal but opposite reaction. For every. He didn't say for some. He said for every. So if you are hitting your cheek is hitting you back. It's just that the cheek is soft. That's why you don't feel pain in the hand. Go with that same hand and hit the wall and you see. You feel pain because the wall is also hitting you back. It's not only the wall that hits you back. Even the chick hits you back. Everything hits you back. So for every action, there is an equal but opposite reaction. That's how you think like a scientist. You control your mind like that. So when we talk about pressure, we know how it affects equilibrium. It depends on moles. If it's temperature, it depends on endo and exo. So if you increase temperature, equilibrium must fight that. So what will happen? It will shift to what? Which one between endo and exo? Which one reduces temperature? Students, which of the two? Does exothermic release heat or it takes in heat? It releases, so it's not a friend. When you increase temperature, we want to take it away, that temperature. So we shift to endo. Write this down. I don't want you to struggle next time. If you decrease temperature, you have lowered the temperature. Equilibrium must fight. So it will shift to exo. It will promote the exo side. Now for pressure, when we talk about pressure, we talk about number of moles. If you increase the pressure, equilibrium must fight you. It must fight. So it will shift to less moles. Less moles to reduce the pressure. It will shift to less moles to reduce the pressure. Then if you decrease the pressure, equilibrium must fight it. So it will shift to more moles. So for pressure, you look at the moles. Here there is 1. Here there is 3. So you look at the total at the left. That's 4. Then you look at the total at the right. There's only these 2. So that's 2. So now we want to find out. This is for the Haber process. We want to find out what happens if we increase pressure in the Haber process. We know that if we increase pressure, equilibrium will shift to less. So in the Haber process, left is where ammonia is. We want more of ammonia. So left is where we have ammonia. For temperature, we were stuck. We needed to make sure we get a lot of ammonia, and also we get it very fast. To get a lot of ammonia, we had to reduce the temperature. But we couldn't reduce it too much because we need the reaction to happen very fast. So we would rather get a little bit less ammonia, but the reaction being fast, so we can get something, because we don't have the time. Here now for pressure is easy. You just increase it. If you increase, it will go to less moles, which means equilibrium will shift to the right. So increasing the pressure will make the equilibrium shift to the right, where there are less molecules or less moles, and thus produce more ammonia. So why do you have such a high pressure? Because for the Haber process, if you have high pressure, you have a higher yield, which means you get more ammonia. But the problem, why we don't increase it too much to 1,000 atmospheres or whatever, is it will become too expensive and dangerous. So we cannot, so we stop at 200. 200 is the perfect pressure. It's high enough for you to get a lot of ammonia, and also in a safe way and in a cost efficient way. Why ion catalyst? So that it can increase the rate of reaction. Okay, we know that it doesn't change the position of equilibrium. It just increases the rate. Anyway, why do you recycle the nitrogen and hydrogen that did not react? When you collect your ammonia, you recycle and take them back to the chamber. Why? To increase efficiency and reduce the cost, because they are expensive. They're expensive. Now we know everything about the Haber process. We are fine. Contact process in the last few minutes. Contact process in the last few minutes. Don't let me down. You are my team. Very important. You are all very important to me. I need great marks from all of you. Contact process is to produce sulfuric acid, not ammonia. So when you put your contact process, please. This is one of the reactions. It's like the main one. Let me say them. So what is hard for contact process? Let me tell you right now. It's 3 stages, but there are 4 reactions that you must know. Do you hear me? Can you all hear me, guys? For contact process, you must know 4 reactions. So I need you to know, to start practicing. For Haber process, it's only 1 reaction to know. But for contact process, you are supposed to know 4 reactions. Right. And they happen at different stages. So let's put the 4 reactions and let's make you know them. Right. We are trying to produce sulfuric acid. So just tell yourself that. Just remind yourself that if you've forgotten. Just remind yourself that we are trying to produce sulfuric acid. So we need sulfur, we need oxygen. Then we will add hydrogen later. So we get sulfur in stage 1. We need sulfur and oxygen. They stand alone. We know that sulfur is a solid plus oxygen. We need them. And what will form is called sulfur dioxide. Sulfur dioxide. This is stage 1. Then we go to stage 2. Stage 2 is now what they were calling the main stage. It's just to make this sulfur dioxide be trioxide. That's the only thing. Okay? Right. Sulfur dioxide plus more oxygen. This is now the reversible one. You get sulfur trioxide. Okay? We get sulfur trioxide. And you should balance it. 2 here and 2 there. Then, last stage, stage 3. 2 reactions, and you are done. Sulfur dioxide to sulfur trioxide, anyone can remember that. Come on. Then, the last 2 stages is, first, we make a crazy big something. We take sulfur trioxide, we mix it with sulfuric acid, which we already have. We want to make more of it. So we mix it, we will get this big thing, which we call disulfuric acid. H2S2O7. Then that is the disulfuric acid. This is sulfur trioxide. Then the last one, water should meet the disulfuric acid. H2S2O7 and form a lot of sulfuric acid, double the amount. So this is your sulfuric acid. You have to know this. Okay? By the way, disulfuric acid, sometimes you meet them calling it oleum in your books. So you should just have this. These are the stages of sulfuric acid. So what of your contact process? What makes some people fail is that they don't remember the stages of contact process. So listen, study smart. Spend the night writing these reactions. I'm going to give you an assignment. I need you to write these reactions. Okay? I need all of you to stay active. Mazrita, are we together? Pakiso, are we together? Good. Good, Mazrita. So now, this one. So I want you to know that the reason they say this is the main equation is it is the reversible one. So it's the tricky one. So we need to make sure we use perfect conditions or else we'll be in trouble. How do we produce the maximum amount of this? Now, this is just like the Haber process, my friends. It is exothermic again. It is exothermic. So we already know that to promote this direction, we need to lower the temperature so that equilibrium will fight and try to increase by going more to the right. By trying to go, it will try to fight and it will go more to the right. Okay? And when we decrease the temperature, we mustn't decrease it too much. Because if we decrease it too much, the reaction will be now too slow. And that is why we use 450 degrees Celsius. So if we talk about the conditions, right? In stage one, here, no, don't worry about any conditions. I want you to know, okay, let me tell you now the conditions which we didn't. We know that for our Haber process, we had our iron as the catalyst. Here we don't have iron as the catalyst. Our catalyst is vanadium. So I want you to write this and say vanadium 5 oxide. You just write this. This is your catalyst. Now, if you see it, it is going to all be in stage 2 where you have the main reaction, the main equation. We only have 3 stages. It's different from the Haber process where we had 5 stages, but the 5 stages had no reactions. Here we have reactions, equations to write, and it happens in stage 2. So this is in stage 2. This is where we are going to have 450 degrees Celsius. Then the pressure will be nothing. It will be 2 atmospheres, almost nothing. Then we say vanadium 5 oxide, catalyst. And you're done. Let's go. Don't let me down. I'm counting on you. Don't throw this away, please. Superstars, you are superstars. Don't throw this away. Here are the things. So now they ask you why. Why do you need 450 degrees? We said it's a compromise between yield and rate of reaction. You tell them if temperature is too low, the reaction will be too slow. If temperature is too high, then the yield will be low because the equilibrium will shift to the left, to endothermic. So you can't increase temperature, equilibrium will shift to endo, and you end up getting nothing. Why only 2 atmospheres? Because listen, let's go here. Let me go in. In this main, we produce sulfur trioxide. This is going to be the main product of our main equation. Now, this sulfur trioxide, please, let me say it like this. If you look at this, if I, did I balance this equation correctly? 2s 4 becomes 6, becomes 6. Yes. Okay, good. Here's the reason. This sulfur trioxide, you must know that when you have sulfur trioxide in a reaction, it is going to be the main product. I'll give you the best way to explain that we'll see when we answer exam papers. But what I know about sulfur trioxide is that in an equilibrium container, when you have an equilibrium container, a lot of the sulfur trioxide, a lot of the gas which will be there is going to be sulfur trioxide, which means us changing pressure has really no effect on the position of equilibrium. It doesn't change the amount. At equilibrium, listen, at equilibrium, the reaction vessel has a lot of sulfur trioxide already. This is what they saw from experiments for this particular reaction. We know that the natural thing was going to be, since here we have, look at how many moles we have. We have 2 moles here. Because for pressure, you look at moles. Look at how many moles we have here. Here we have 3 moles. So for us to make more, we were supposed to increase the pressure, Increasing the pressure was going to force it to go to less moles, which means go to the right, and we'll get more of this 2SO3. But naturally, there's a lot of it. Let me see where I wrote it. Naturally, there's a lot of it here. The equilibrium, at equilibrium, this is from an experiment they conducted. They saw that 96%, 96% of what is in your vessel will be already SO3, even at a low pressure. So high pressures don't really help us. We don't need them. We don't need them. We already have a lot of SO3. So it will just increase the cost and safety problems and safety risks. So there is no need for high pressure in the contact process. And you'll be done. You should say that, and you'll be done here. So we are going to test our knowledge by doing past papers. We talked about rate of reaction. We talked about redox reactions and the 7 ways to see. I'm going to give you those important pages, the pages that I feel are important. I should send to you. The page which tells you the 7 oxidation state rules. The page which summarizes the things that can affect the rate of reaction, which we know that it's a lot. The temperature increases. When you increase temperature, you increase the rate. When you increase pressure, you increase the rate. That's for gaseous reactions. When you increase the concentration, you increase the rate. That's for a solution, a reaction which takes place in a solution. When you increase the surface area, you increase the rate. When you add a catalyst, you increase the rate. So 5 things affect rate, and all of them, when you increase them, they increase the rate. Okay, when you have more of them. But for equilibrium, it's only 3: concentration, pressure, temperature. Those are the only 3. So you should know the 3 things that affect rate or equilibrium versus the 5 things that affect rate. You should know the 7 oxidation state. You should know the conditions of the Haber process and the contact process and why we use them. I want you to master these things. We're going to questions. We are going into questions. And you're not going to let me down. You're not going to let me down. So I'm going to, seems like you guys now know, I'm going to do I'm going to send them the summary of the important documents plus this. And we do questions in our next chem lesson on these. A lot of questions. Paper by paper. Paper by paper. Anything which asks about rate and collision theory, we answer. Anything which asks about the Haber process, contact process, we answer. Anything which asks about equilibrium, we answer. Rate of reaction, we answer. Redox, we answer. We're going to be doing together, and we see how much we can get. Let me mark this register as the last thing. And we'll see how good we are. We put ourselves in the acid test. We see, are we good or are we not? Are we together? We'll test ourselves.